Hello students, I am Preeti Kapoor from Bullseye. I have a teaching experience of around 14 years. In this session, we will talk about functions. Now, functions is a highly theoretical concept with huge practical applications. In this session, you will learn the definition of a function, domain, codomain and range of a function, types of functions and important properties, the inverse and composition of functions, some problems based on the theory, and in the end you will have some practice questions and the answer key. Now coming to the definition of a function is a relation from a set A to a set B such that for each x belonging to A there exists one and only one y belonging to B. Now to understand this definition better, let's take its graphical representation. Let us take this set A and a set B. Then every element belonging to X must be related to one and only one element Y belonging to B. Then this Y is called the image of X and the X is called pre-image of Y. The set A is called the domain of the function and the set B is called codomain of the function. Now to further understand this definition better, you have to focus on the fact that what makes a relation fail to be a function. Now if I have a situation where a relation from set A to set B is such that there is a member X belonging to A for which there is no image in B, then this fails to be a function. Second situation is if I have a relation from set A to set B such that there is an element X belonging to A which has got two or more than two images in B, then this again fails to be a function. Also focus on the fact that the conditions that we have laid down for a relation to be a function are on the elements of A, and the condition says that for every X belonging to A there has to be one and only one Y belonging to B such that the ordered pair X comma Y belongs to F, and we can write this as F of X is equal to Y. These conditions are not imposed on the members of the set B. That means if we have a situation where there is an element P belonging to B which is not the image of any member of A, then this does not violate the definition of a function. Also, if I have two different members of the set A having the same image in the set B, this again does not violate the definition of a function. So remember, these two situations are allowed in a function. Next we have range of a function. So range is basically collection of all those elements of B which are the images of some elements of the set A. That is, let's again understand it graphically. Suppose I have a function from set A to set B such that the element A has its image as P, the element B has its image as Q, and there is an element R in the set B which is not the image of any element of A. So this is a function. Now here the entire set B is the codomain of the function, but in the range we will have only those elements of B which are the images of some elements of the set A. Therefore in the range we will have only the elements P and Q. R will be excluded out of the range. Next definition is a function from A to B is called a real function if both the sets A and B are subsets of real numbers. Now coming to the kinds of functions, the first one is many-one function. A function from A to B is said to be a many-one function if two or more elements of set A have the same image in B. That is, if you take up the mapping from A to B, which is a function, is said to be many-one if suppose I have two or more than two elements in the set A which have got the same image, let's call this image as Y, in the set B. So we can understand and remember this by saying that many elements of A are going and getting related to one element in B. The next one will be a 1-1 function. So we can simply understand that a function which is not many one is in fact a 1-1 function. So 1-1 function is basically the opposite of many one. That means a function f from A to B is said to be a 1-1 function, and the other name for 1-1 function is injection if different elements of A have different images in B. That means if I have an A related to P, I have a B related to Q, no two different elements of the set A are being mapped to the same element in the set B. So this kind of a function is called a 1-1 function. Next is an into function. A function f from A to B is said to be an into function if there is an element in B having no pre-image in A. That is, a function from A to B such that there is an element or more than one such elements in the set B which are not the images of any element of A. So such an element I have taken as P here. So suppose A is getting mapped to say R and B is getting mapped to say Q, but P is not getting mapped to any element of A. So under such a situation, this function is said to be an into function. Next one is an onto function, which is also called as surjection, and it is in fact the opposite of into function. So a function which is not into is said to be an onto function. That means in this function there will certainly be no such element left in the set B which is not the image of any element of the set A. Also, a very important point here is that if it is an onto function, then there is no member in B which is not the image of any member of A. Under such a situation, the codomain will always be equal to the range of the function. So you can see that if a function is a surjective function, then the codomain will always be equal to the range of the function. So here we have written that the range is always same as the codomain of the function. So to sum it up, we can have following 4 types of combinations and 4 types of functions. The first one is 1-1 and onto, which is also called as bijection, and is the most important type of a function. The second one is 1-1 and into, third is many-one and onto, and the fourth one is many-one and into. So let's take up the 4 situations and identify the type of the function. So suppose I have a function from a set A to a set B such that I have this kind of a situation. So I can easily see that there are 2 elements of A having the same image in B. So that makes it many-one. I can see that there is no element in the set B which is not the image of any member of the set A. Therefore, it is an onto function. So which makes it many-one and onto. So let's name these as A, B, C and PQ. Let's take another situation where I have something like this. Now we can see that different elements of the set A are mapped to different elements of the set B. So it is a 1-1 mapping. Also, there is a member in the set B which is R that is not the image of any member of the set A. Therefore, it is an into function which makes it 1-1 and into. Let's take a third situation. Here again you can see that many members of the set A are having the same image, that is P, which makes it a many-one function. Also, there is a member which is Q in the set B that is not the image of any member of the set A, which makes it an into function. Therefore, it is a many-one and into function. Now let's take this situation. Let's take this element as A, this is B, this is P and this is Q. Now different elements of A are mapped to different elements of B. That makes it a 1-1 function. Also, there is no element in B which is left unmapped, which makes it a onto function. So this is a 1 and onto function, which is the most important one, and we gave another name to it, which is a bijective function or simply a bijection. Now the next definition is inverse of a function. Please remember that this definition is valid only for the functions which are bijective. So if f is a function from a to b, which is a bijective function, then f inverse is also a function, but it is from the set b to set a, that is, it is reversing the function f, such that if fx is equal to y, then f inverse of y is equal to x. You can notice here that we are using the symbol f inverse for the inverse of a function. Now again, let's understand it graphically. Let us suppose f is a function from the set A to a set B such that it maps the member x to member y. Then we write it as f of x is equal to y. Now the inverse function will map the member y to member x. That is, f inverse of y will be x. So basically we are going in the opposite direction. So in f we were going from x to y, relating x to y, and in the inverse mapping we come back from y to x. Next definition is the composition of functions. Now if we have suppose two functions, let's take f is a function from a to b and g is a function from b to c, then the composition of the two functions g of f is from the set a to set c and is defined as this. So again, let's understand it by taking the mapping. So f is a function from set A to set B and g is a function from set B to set C. Then g of f is again a function from the set A to set C such that for every x belonging to A, g of f of x will be nothing but g of the answer of fx. That is, suppose fx is equal to y and gy is equal to z, then this answer will be g of y, which is z. These are some important properties of functions. The composition of functions is not commutative. That is, f of g is not always equal to g of f. Now the second property says that the composition of functions is associative. That is, if I have three functions f, g and h, then f of g of h is always same as f of g of h, provided both of them exist. The third property says that the composition of a function with identity is equal to the function itself. Fourth property says that the inverse of a bijection is unique and is also a bijection. The fifth property says that if f is a function from a to b and is a bijection, then f inverse is a function from b to a. In that case, if I take the composition of f with its inverse, then it will come down to be a identity function. If f is a function from a to b and g is a function from b to c and they both are bijective functions, then their composition g of f from a to c is also a bijective function, and the inverse of their composition will have the product, or we can say the composition in the reversal law. That is, g of f inverse will be f inverse of g inverse. The next property says that if f is a function from a to b, which is a bijective function, then the inverse, which is represented by f inverse, will have an inverse which is equal to the function itself. So which basically means that the inverse of the inverse is the original function itself. Now let's take up this question. Now in this question we have to identify that which option is not making a function. Now remember the definition of function. It says that for every x belonging to A, there has to be one and only one y belonging to B. So we have to identify which option is violating this rule. Now coming to the first option, x square is equal to y. Now we know that for every real number there is one and only one square, right? So for every x I will have one and only one x square, which will be the image of this x. So this will certainly make a function. In the second option there is a problem. For negative x in the domain, there will be no such y for which I can have y square equal to x. Why? Because y square will always be a positive number. So it can never be equal to a negative x. So for example, I'll have minus 3 in the domain, which will have no image in the codomain. So this certainly fails to be a function. In this question, we are given that g is a real function, and this is how the function is defined. We have to find out the domain and range of this function. Now, as we understood in the definition, the domain is the set A and the range is that part of the set B which is the image of some elements of A. So the domain will be the entire set A for which this expression is valid, and you can easily observe that this expression will not give me a real answer for x equal to minus 3. So my domain cannot have minus 3, but it can have all other real numbers. So the domain will be the set of real numbers excluding the number minus 3. Now coming to the range of this function. For range, we have to basically find all those y's belonging to B which are the images of some x belonging to A. So let's take y as the image of x, then I'll have y is equal to 1 upon x plus 3. So if I solve for x from here, I will have x is equal to 1 upon y minus 3. That means for every y, I will have an x provided this y should not be 0. If y is non-zero, then there will certainly be an x such that the image of x is y. That means the range of this function will have all real numbers except for the number 0. Okay, so you can see the answer here. Now, in this question, we are given that f is a function from real numbers to real numbers, and this is how the function is defined. I hope you know this symbol. This is basically the greatest integer less than or equal to x. Then we have to find out that which category this function belongs to. Now to see this, let us take f of 0.7. So the way fx has been defined, it will be greatest integer 0.7 square plus greatest integer 1.7 minus 3, which will be 0 plus 1 minus 3. If I take f of say 0.6, I will have greatest integer 0.6 square plus greatest integer 1.6 minus 3, which will be 0 plus 1 minus 3. Both these answers are minus 2. That means 0.7 and 0.6 in the domain will have the same image, which is minus 2. That makes the function as many one. Now we have to find out whether it is onto or into. Now you can easily see that this is an integer, this is also an integer, and minus 3 is also an integer. So this sum, which is the definition of fx, will always give integer as the answer. That means in the codomain, I will have only the integers that will make the range of fx. So the non-integers will not be the image of any member of the domain. That makes the function as into. So we get the function as many one and into function. Now in this question, we are given the function fx as x plus 1 by x, and we have to find out the f inverse. Now be very careful in these kind of questions where you have to find the inverse of a function whenever there is an option of the type none of these. Why? Because we learned in the presentation that the inverse exists only for bijective functions. So if the function is not bijective, then you will have to mark none of these as an option. But such an option is not here in our question, so we can easily assume that the given function f is bijective and the inverse is certainly existing. Now to find the inverse of a function, there is a systematic procedure which is followed, which has 3 steps. The step number 1 says that write fx as y. Step number 2 says that solve for the value of x in terms of y. And in the third step, we interchange x and y to get the rule of f inverse of x. Now, why are we doing this? Because in the definition of the inverse, we learned that if f is a function which takes x to y, then inverse will take y to x. That means f inverse of y will be equal to x. Therefore, we solve the value of x in terms of y to get the rule of f inverse. And to finally write the answer not as f inverse y but to write it as f inverse x, we do this interchanging thing. So if we follow the steps here, in our question fx is given as x plus 1 by x. So x plus 1 by x will be written as y. That is step number 1. So I can multiply the entire equation by x because we are given that x is not equal to 0. So this you can see is easily a quadratic in x, which we can solve for the value of x. So the value of x will be, now if we interchange x and y, this is what we get. But still there is an issue here. Now to understand this confusion, remember that the definition of function says that for every x there has to be one and only one y. So it has to be either plus or minus. Now to get rid of this confusion, we go back here and see this. The domain of the function f becomes the range of f inverse. So that means under the rule of f inverse, the answers have to be more than one. So I will have to take the positive one and ignoring the negative one. So the answer has to be x plus under root of x square minus 4 whole divided by 2. So which is nothing but the first option. In this question we are given fx as x square and gx as 2 raised to power x. We have to find out the solution set of the equation f of g of x equal to g of f of x. So first of all, let us write what is f of g of x here. So f of g of x is nothing but f of gx. Now what does gx do for us? Gx takes 2 raised to power x. And what does f do to its input? It makes the square of its input as the answer. So if I give 2 raised to power x as the input to f, it will basically give me the square of this number as the answer. Now come down to g of f of x is g of fx. Fx is defined as x square. Now I have to apply g on this, and what does g do to its input? G basically takes its input raised to power 2. So I will have g of x square as 2 raised to power x square. So this is g of fx and this is f of gx. We are asked to make them equal and solve for those x which satisfy this equation. So I will have 2 raised to power x square equal to 2 raised to power x whole square, which is 2 raised to power 2x. So to make them equal, I need the powers to be equal, that is x square has to be equal to 2x, which you can easily see is being satisfied by two values of x, that is x equal to 0 and x equal to 2. So the solution set is 0 and 2, that is the third option. Now these are some of the practice questions. And this is their answer key. I hope this session will make you comfortable in solving questions based on functions. Thank you.